Okay, welcome. Today we're going to be going over a tool that Jeff and I built for fluid combustion solving that allows for dynamic erosion slash evaporation of collision objects. We have a simple example that illustrates the tool's capabilities, and we'll go over some of the parameters in the solver and some setup requirements, I guess. There's a bunch of notes in this file, but I think with the example file you can read that. I'll talk a bit about a bit about this file itself. So this top note, this example shows how a point cloud can be turned into a collision object and eroded inside the FC solver. That's our name of our solver. We have set the output to output collision field so you can see what is happening, and we'll get to that. So to start, we've got a sphere that we plug into this pop net and scatter points onto the surface, and then use a pop force to create some velocity. And what this gives us is like a simple flamethrower source, essentially. After the pop net, we create some attributes. I don't think we actually need density, but we do need fuel. One of the requirements of our solver is having a fuel attribute. Actually, one of the requirements for combustion, proper combustion in our solver, is fuel. You don't have to have fuel. You could plug in density and it would sim, but you wouldn't get any combustion. Next, we have a fire attribute that we're creating. We'll get into why we create that in a minute. Next, we're noising fuel just because it looks cool. I'm trying to get like pockets of fuel that move with it. Okay, cool. So this is kind of important. We've got, turn fuel off, we've got an ignite group, and what that's doing is saying, hey, we want to pick where we want to set temperature. Temperature is a required attribute for combustion as well. This switch is just saying, hey, we're going to have our particles exist for 24 frames. The stream's going to get going before we introduce temperature. We're adding some velocity noise. I don't know why that's blue. What am I viewing? I see. You just can't see because they're in the points. Okay, so adding some velocity noise. Time blend, just so we can get subframe data. And then we're rasterizing temperature, velocity, fuel, and fire. The two things we have to have for combustion are temperature and fuel. Need velocity so we can have the sim work properly, I guess. And what that gives us is this. Okay, cool. For this example, it's low resolution. 0.075. I don't know what I have this set as. 0.075. 0.1. Okay, so I think this is just for sim speed, but okay, so this is our FC solver, and it's not too different from like this SOP pyrosolver. There's a lot of the same tabs. I think the only ones that we have that are different are evaporation and shaping is, I think we've called shaping, we've labeled it different. So here's like a surface level difference, like just right, you open it up and this is what it looks like, the differences. So not too different. There are some, oh, we have combustion as well. Okay, so like these three, evaporation, combustion, sourcing, are different, or shaping, sorry. And then some of the parameters inside these tabs are potentially labeled different, but the UI is similar. Okay, so what do we have going on here? Like, why are we creating this thing? What is the point of this solver? On a like surface level, we wanted to be able to erode and evaporate a material using pyro, and we wanted to do it in the same simulation. So I'm going to come back to that. I think for now I want to go over just a quick overview of each tab. We have this default tabs, which is like, shouldn't have to mess with any of this stuff initially. Look around, of course, do what you want, but shouldn't have to change anything in this default tabs. In the setup, you control substeps, voxel size, velocity, voxel scale, so you can make this bigger if you don't need, like you have a huge sim and you don't need velocity to be as high res, then you can control that here. Control viscosity, wind, and gravity. This is kind of like, yeah, the basic parameters. Next we have bounds, which we have the option to control the maximum bounds with this toggle here. If we don't have that, then the bounds can get bigger than this. That's all that means. For collisions, we have a toggle that allows us to use a ground plane. Right now it's on. And then we also have, you can plug a collision into this. Let's see. We'll call this collision. We'll move it. Go back just a bit. Okay, so what does this look like? Okay, so we have our collision, SDF. We can see it here. If you want to use a collision, you just plug that into the right side of our solver. And you just need to make sure that whatever you've named your collision SDF matches here. We don't have any velocity on this object, it's not moving. But if you did, you would do the same thing. You would, let's see. You would just have to make sure whatever you named your velocity field, make sure it's here. We don't have it, so we can turn it off. Okay, so what does that look like? Take just a minute, see if it hits it. Okay, so we're outputting collision, so we can see it's being treated as collision. Doesn't really look like it's, well, maybe it's because it's on the inside? No, it is hitting it, okay. Okay, so I'm going to turn this to invisible real quick. Yeah, okay, so it is hitting it. It's kind of going through it, but... oh, maybe it's not going through it at all, actually. Anyway, so that's how you would plug in collisions. If you had multiple of these, you would have to merge them. Let's say, let's bring this up to 5. So I think this is the only way that it will work. It's possible that it doesn't. So you drop a VDB merge and that creates one collision field. If you just drop a merge, there will be 2 collision fields. It's possible that it will treat it properly. That's something you can test, but if you need 2 collision objects, I think it's best to merge it. I guess let us know if you discover something different. Okay. So what is that? Right. Let's go to the next thing. So we're talking about collisions, and for this example, we don't actually need any. Next, we've got an evaporation tab. Just set the sim. Okay, what is evaporation? This is controlling evaporation of our whatever object you want. In our case, we have a wall of points that this beam is going to interact with. We have the node path in this source particles parameter. And okay, so what happens here? Essentially, this, using these parameters, temp, diffuse, evaporation scale, water scalar, and then relative density, sourcing, and collisions, we get to control the erosion of these points. Okay, so what does that look like? I have one example simmed out, and I've exported collisions, turned it into a polygon, and I have pyro, just a pyro bake volume to visualize it. And you notice you can't see the collision before it interacts with the pyro. That's just to save for calculation, so we don't have to create collision objects unless it's interacting with pyro. But if you look closely, we can see that this thing is like there's like a dent in it now. And if we go far enough, the pyro will eat through it. And it'll look something like this. And then it breaks through. That's pretty cool. There's a lot of things you can do with that. So I have this as like an example of what the collision looks like not eroded. And just to like show you, hey, there's a big difference between these two. Like this is clearly being evaporated or eroded by the pyro simulation. And yeah, it's pretty cool. Okay, so what do these parameters inside the solver mean? There's some help notes. We don't have them all right now, but if you don't want to evaporate, like when we play this, you don't want to have evaporation, you turn it off. We basically, the pyro is not going to interact with anything because there's no collision object and there's nothing to evaporate. I think this is probably far enough. Okay, so we can see the previous collision, but now we have pyro just going straight through. We go to output and we change this back to isosurface, and the only thing that we have now, you can kind of see it, is the ground plane. Okay, and that's important because whatever you plug into to enable evaporation, whatever you plug into here is going to be treated as a collision object, which you control the settings here. It's very similar. It's same user interface as like a VDB for particles. And you can control, you know, just like a volume source node inside of a DOPSIM, you can control how you want to apply velocity if there is a velocity attribute on your particles. These are static, these don't have a velocity attribute, so this stuff is like, there's nothing happening here. There is no V, so there is no collision velocity being created. Next, I guess I'm going out of order, but we have temperature diffusion, which is how fast the temperature is traveling through the particle, the point cloud, if you will. Another way to describe it is like the particle is going to absorb like 10% of the temperature of the sim each time step. Or maybe it's per second. No, this is time step. This is time step. So over 10 frames, it is going to be, it is going to have a value of, if there's one temperature each being applied to it each frame, and it absorbs 10% of it, is going to take 10 frames for the point's temperature value to equal 1. That's a lot of words, but how fast temperature spreads in your point cloud. Evaporation scale is like, we have created an evaporation number, if you will, an attribute. This is a direct scalar on that. So like, let's say you like the spread of something. This is, you like the spread of the temperature values. This is like a direct scalar on, hey, I actually like this. I just wish it was 2 times faster or 50% slower. You can just scale. This is like an overall scalar, if you will. And then water scalar is similar to if, like, we have temperature, V, fuel, and fire. Water, this is like a direct scalar on the emission of that, our water field, which is this. So, let's make it easier to see. And like, what is water field? Water field is the field that we're creating from the object we're evaporating. And for right now, like, it has to be named water, but we'll make it so the user can control that in the next version. The next thing is use relative density. For this, it doesn't matter so much. Like we could probably even turn it off. It's not going to change a thing. But this is a value of 0 to 1. And this is like how particles that are by themselves are going to erode faster. They're going to burn up faster and emit water sooner than particles that are really dense. Sourcing. This is sourcing for our water field. The field that this is sourcing for the field you're emitting when you enable evaporation. And this voxel scale is like, this is a scalar on the sim resolution. So this is like 0.1 times 0.6. Yeah, that's pretty much it. These are just controls over if you have evaporation enabled or want to evaporate an object. We have inject pressure here, which is kind of cool. It allows us to, hey, we have a bunch of water here. If we want to inject pressure, what happens is we have it labeled steam sourcing now. This activation goes to 1, and we turn our water field into pressure, and then add that to the divergence field. So this can create like a boiling effect, which can look really, really cool, especially if you're emitting a ton of steam. It can look really, really cool. Next, we have combustion, which I don't know why I brought these up, but don't touch. You can probably mess with this one. This acts similar to like a temperature diffusion, but we have to have this in here for the combustion solver to work properly. Probably best to leave them alone for now. This is pretty simple. There's not a lot of parameters to mess with. First, we have burn multiplier, which is how much fuel you want to remove per voxel at each time step. So if you want your fuel to go away quicker, here's a way, like you want your fuel to burn faster. This is where you control it. We have ignition temp. The help is right on the money. If temp is below this threshold, no combustion occurs. And then, so we use this to scale burn, which is added to the temperature field at each time step. So you could make this, like this would make the sim 3 times hotter. The temperature values would be 3 times greater. I think 1 is like accurate. It will 1 is probably the best thing, but if you needed it to be really hot, you could change it. The sourcing is split into 2 sections. We have steam sourcing, which is what you see here, and this only turns on when you have enable evaporation. Now it's disabled. It's enabled again. It's the same kind of structure as a normal SOP pyrosolver. The only difference right now is that we're forcing, essentially in this version, to the source volume has to be water. The target field can be anything. It could be steam, it could be plastic, it could be organic material, it could be whatever you want to do. The source volume has to be water right now. because of how we built it, this will change. Everything else is pretty much the same as normal sourcing. We have a temperature field. We have velocity on our steam source, and then this is what we talked about earlier, where we can enable pressure if we want. For our fire sourcing, for the pyro to work, we have to have a couple fields. We have to have fuel. For fire, you don't have to have this. We recommend you have something to distinguish between the two. By between the two, I mean between the water and so here's fire itself, which is, we have a way to separate water and fire. Like, yeah, we could use temperature, but temperature encloses kind of both water and fire. So creating an additional field allows us to separate the two. And that kind of goes into the next topic. For now, we'll finish this fire sourcing, and it is, again, we have to have temperature and fuel, and we need velocity for it to behave properly. Okay, so we have a shaping tab, and this is similar to the sourcing, where we split it into two sections. This is kind of where that fire field comes in, and it allows us to apply disturbance and shredding and turbulence specifically in areas of the sim where, let's say, our water is looking good, but we need to break up the beginning of the simulation. We can just apply some sort of shape operator to using this case speed as a control, and our threshold field is fire, so it's going to be applied to the edges of the beam. And another thing that we've added is an additional control field. So this operates the same as the control field, essentially, where we can look at our water field and say, hey, if water is 1 or 0.1, we want 0. We want 0 of this applied to it. We want 0 of this disturbance applied to it. For now, we'll leave it off, but that's what that does. We have more control here. You can, you just have more control. So, and that's for each. That option is for each, disturbance, shredding, and turbulence. For disturbance, we have a primary disturbance and we have a secondary disturbance. So this allows you to apply multiple levels if you decide. And multiple levels of disturbance and shredding. And then same with turbulence. You have the choice. You can disable this. If you only want one level, you can disable turbulence entirely. So now you can't, there's nothing applied. And that's pretty much it. For the main field shaping, we've labeled it this way and split it into the section. So hey, you could apply for your main pyro beam, you could apply all your shape operators here. And then for evaporation fields, you could just apply them here. Something to note is that these don't automatically know that I don't want to operate over a temperature, or I don't want to operate over fire. Like, you have to tell it that, and like here's a way to do that. You could say additional control field is fire. We're going to remap it. We don't want. How do I flip this? Okay, so basically, if there's greater than 0.1 fire, we don't want to apply this disturbance. So I think I can build a quick example of that. And what that would be is just do a new geometry node. Scatter. Okay, so then we're going to need at fire equals 1, f at and then set v at v equals set 0, 1, 0. Okay, so like we'll initialize some attributes here. And int attributes. And then, so we have that. Volume rasterize. Volume rasterize attributes. Fire, temperature, V. I think that's fine for now. Maybe make this bigger. Maybe make this 0.1. And then I'm going to grab this solver. Okay, so we have the same settings. So I don't need evaporation. I can come back to sourcing. This is going to be disabled. I don't actually need fuel for this example because I'm not doing any burning, but if I turn this to 1 and subsets to 1 and play this, should be pretty fast. Okay, what is there? Turn off max bounds. What is this? Okay, this is airing. Why is this airing? This is good. because some things just don't. This breaks, I guess. Shaping. This should be off, which is fine. Unknown parameter. What the heck? Alright, what if I... Okay, so we have fire. Doing this live might not have been the best idea. But I feel like it's more realistic. So this pull 50 v val vector maximum use vector length. Okay, so we have our source. Shaping is, we're just gonna disable shredding and just keep turbulence enabled. Voxel size 0.1. I don't need a ground plane. Okay. Hopefully this works. No errors. Where's the... Where's the freaking thing? Fire temperature V. We can see it. Invalid source. Might have to restart Houdini. What the? Okay, I'm gonna close Houdini and open it back up.